Hi, my name is Chia-Wei Hsu. I am a PhD research assistant of Resilience.ai Lab from the Civil Engineering Department. My term project title is Exploring the Trend of Disaster Resilience Research through Topic Modeling. I will go through introduction, data processing, exploratory data analysis, methodologies, results, and conclusion. Disaster management and resilience-related research topics and applications have been more critical than ever as the climate has become more extreme and the frequency of natural hazards and pandemic increases rapidly. Research to mitigate the damage and accelerate the recovery process have made a significant impact on multiple aspects. For example, preparedness, resiliency, and accessibility. However, some problems remain unsolved and some parts of the world did not receive enough attention and resources. To address this concern in some manner, we want to understand the trend and topics that received most attention or overlooked in the disaster resilience field. Unlike the 2022 data science competition challenges held by Texas A&M Institute of Data Science, the dataset used in this study specifically focused on one research field, disaster resilience. In order to collect the metadata from the best papers in the field, we select the highly rated journal, International Journal of Disaster Reduction, and then scrap its metadata from the ScienceDirect website, powered by their publisher, Elsevier. We take a lot of effort to scrap the raw data and then transform it into a clean table format with the BibTeX parser for further analysis. Total 2,488 articles before April 2022, and their metadata including topic, authors, years, abstract, keywords alike are collected. We could first do some exploratory data analysis to see the big picture. The number of papers published has gradually increased since the first issue published in 2012. The increasing trend may due to the reputation of journal and more attention on disaster resilience. Another observation is the significant jump in 2020, probably due to the outburst of COVID-19 pandemic. Here we provide some data samples. We only focus on text, so we keep the essentials, including title, abstract, authors, year, and keywords. In the titles and abstract, we first perform some simple cleaning to remove punctuation, lowercasing, and exclude low frequency or meaningless words in terms of analyzing. The word cloud generated unsurprisingly show the word with highest frequency, including disaster, risk, resilience, flood, earthquake, and so on. The next step, we do the tokenization and lemmatization with the natural language toolkit. What tokenization do is to chopping a character sentence into pieces given a defined document unit. The generate tokens often refer to words, while lemmatization reduces inflectional forms and sometimes derivationally related forms of a word to a common base form. So the simple examples like turning plural to singular form, or the MR is to the be verb. After all data processing is completed, we rank the most popular words in titles and abstracts, respectively. The commonly shared words are disaster and risk, same as what we saw in the word clouds. Other high-frequency words have something to do with disaster types, including flood and earthquake, and the aspects of disaster risk reduction, including resilience, management, community, vulnerability, recovery, and preparedness. The next step is word embedding. We vectorize the collection of words from the papers using Word2Vec. It gives us vectorized presentation of text. Individual words are transformed into a numerical representation of the word. Each dimension represents some aspect or characteristic of a word. The T-distributed stochastic neighbor embedding, the TSNE, help us with dimensionality reduction and sometimes give good visualization that we can see the clusters on a 2D graph. Its idea is that similar words will have similar vectors, and those words will be closer in the vector space. The model we use in the topic modeling study is the latent dirichlet allocation LDA. It is a Bayesian generative method. Our problem would be a classification of processed abstracts. Our objective is to discover the hidden themes or topics, then classify the papers into those discovered topics. Topics are a group of statistically significant words within a corpus, and we'll see which topic is dominant for each paper. Here we take a brief look at the Dirichlet distribution. It is a multivariate generalization of beta distribution controlled by alpha values. In the 3D visualization, we see that large alpha push the distribution to the center, while smaller alpha push the distribution to the corners. Let's explain what topic modeling with LDA does in a simple manner. Let's say having a set of M documents. Each document has N words, which each word is generated by a single topic from a set of K topics. We look at the joint posterior probability of data, Z and beta, given data document topic distribution and topic word distribution. Theta is distribution to topics, one of each document. Z is the collection of topic of each document, and beta is the distribution of words, one for each topic. Before diving into the details, let's get a few things across, like notation and definitions. So the model parameters alpha control per document topic distribution, beta controls per topic M distribution. M is the number of documents in the corpus, N is the number of words in each document, W is the word in a document, Z is the latent topic assigned to a word, distribution of words. Let's say animal could be 0.3 cats, 0.4 dogs, 0 AI, 0.2 loyal, and 0.1 evil. And K is the number of topics a document belong to, which is a fixed number, and V is the size of vocabulary. We have a single alpha value which defines theta. The topic distribution for documents is going to be like, we have M documents and got some theta distribution for each document. Assuming there's only a single document, it has N words and each word is generated by a topic. We generate N topics to be filled in with words. Based on beta, phi has some distribution, a Dirichlet distribution to be precise, and according to that distribution, phi generates K individual words for each topic. Now we can fill in a word to each placeholder in a set of N placeholders, conditioned on the topic if it presents. The probability we discussed above is very messy, so we cannot calculate that on paper and have nice equations. So we're going to approximate that with some known probability distribution that closely match the true posterior. The way to do this is to minimize the KL divergence between the approximation and true posterior as an optimization problem. Gamma, phi, and lambda represent the free variational parameters we approximate theta, Z, and beta with. We evaluate the model by topic coherence. It measures a score of a single topic by measuring the degree of semantic similarity between high-scoring words in the topic. There are not much differences on the coherence score when we choose different number of topics. Probably the number of samples are not enough and they might have high proportion of common contents. For the purpose of interpretation, we choose 4 topics. The figures show the word count and their importance or weight in the topics. We still see some common terms, but the secondary important words may give us some insights. We can conclude what are the important ingredients in each topic by observing the word cloud generated from word count and importance. The majority is topic 0. We see that the contents of topic 0 are more general disaster resilience, which do not necessarily involve in some specific context. The second most is topic 3. These are the most recent issues that draw more attention related to housing problems and the COVID-19 pandemic. The third most is topic 2. We can clearly see that the focus of this group is earthquake and building structure concerns. And the fewest is topic 1, which has something to do with flooding. The number of papers clustered into each topic may have something to do with their publication year. We know that the number of publications are more than the first few years of that journal, and that makes the recent papers being weighted more. As what I just mentioned, weighing the time factor might be a concern. Perhaps we should also including other journals to increase the size of literature database and increase the diversity. Another idea related to graph learning may be constructing collaboration network and incorporate network features to predict future collaborations and research trends. We also found that equity and accessibility topics are overlooked, as we always consider it important in our professional sense. This is the end of my presentation. Thank you.